Hello everyone. I'm glad to have the opportunity to talk at this meeting. The title of our presentation is Validating the Redundancy Assumption for HDL from Code Column Perspective. There are 5 parts in this presentation, including motivation, approach, research questions, results, and conclusion. Hardware description languages has entered the golden age. In the semiconductor sector market, FPGA reached about $5 billion in 2019 and is expected to reach $7.5 billion in 2030. Thus, the market for FPGA is gaining importance. However, in 2020, 83% of FPGA projects have bugs escaping into production, and more than a half of FPGA project time is spent on verification, among which almost a half verification time is spent on debugging. Therefore, debugging on hardware design code is a time-consuming task, which also affects the production issue of hardware. This naturally raises an urgent need to propose advanced automated program repair techniques, named APR, to add debugging activities of HDL. APR aims to repair defects without human intervention, which has attracted a lot of attention of researchers in hardware, such as Surface. In patch generation, Surface adopts a generator programming with predefined repair templates to generate patches. Furthermore, we observed that such search-based program repair techniques use existing code fragments to generate patches, which is based on the redundancy. The assumption has become the basis in the APR techniques. However, we found the redundancy assumption had not been validated in HDL, which had the development of the APR techniques targeting HDLs. Redundancy assumption is that the code fragment for bug fixing already exists elsewhere in the code. For the above example in list 1, it involves updating assignment statement. In the example, the buggy code is a modified assignment statement, highlighted in red, and the donor code is a concrete code for patching, highlighted in green. Then formally, we can define the redundancy assumption to be that there exists some donor code that can also be found in the original program. Unfortunately, there are only a few studies related to the reputation of hardware design code, and almost none studies have been done on the redundancy assumption for automatic program repair in HDL. The problem is whether the donor code exists in the original buggy program. Furthermore, it's unknown how to search for the donor code. We tend to validate the redundancy assumption from code clone perspective, as type 3 clone refers to the copied fragments with further modifications. Donor code could be found in the code clones of buggy statements. Therefore, we propose vclone to extract and detect the clone of bug fix in Verilog automatically. Firstly, the study is to validate the ground truth of .NET code being in the original program. Secondly, is to explore the .NET code availability from code clone perspective. Based on the clone detection, it will be likely to detect clones that meeting the following two requirements. The code contains a buggy statements, and the clone are similar. The clones contain the .NET codes. As for the buggy fixing code change in listing 1, we can fragment the program and obtain the buggy code snippet. Buggy code snippet is a snippet that involves code changes, contains the buggy statements, and its code contents, as shown in list 2. And the code clone patch contents refers to the code clone of buggy code snippet that contains the .NET code, as shown in list 3. We can observe that the code contents of listing 2 and listing 3 are similar. While listing can provide the .NET code in the example. Motivated by the example, we performed the study to explore the redundancy assumption in HDL. The overall workflow of our approach is as shown. Finally, we retrieve bug fixes from the open source Verilog projects. In the phase, we can collect related .NET codes. Secondly, we fragment the buggy program to obtain all snippets containing buggy snippets. Then we can detect code clones of buggy snippets using an open source code clone detection tool, SourceCC. Finally, we perform the analysis on code clones. If one clone contains the .NET code, we concede that it can be used for generating patches, and define it as a code clone patch context. Following the above steps, we conduct the experiments on several open source Verilog projects from GitHub, as shown in Table 1. The purpose of this study is to validate redundancy assumption in HDLs from code clones perspective. Therefore, we want to investigate the following two research questions. The first question is about redundancy assumption. We want to figure out what extent are code clones or patch contents in Verilog projects. The second question is to analyze the distribution about code clone or patch contents, from which we can obtain useful knowledge about bug fixing in HDLs. As a result, we measure the redundancy of buggy snippets. The table shows the mean value of redundancy on buggy fix commits and add the statement with global and local scope respectively. For the global scope, the buggy snippet is a global redundant if the corresponding code clone patch contents can be found elsewhere in the program. For the local scope, the buggy block is locally redundant if the corresponding code clone patch contents is from the same file. The measurement in global and local scope can facilitate the analysis of search space and search efficiency of the .NET code. In the global scope, as we can see, the clone coverage of bug fix as global scope is about 17.7%. which also validates redundancy assumption in HDLs. Although the percentage of code clone is not high, it can also bring values to society and community if a fraction bugs can be fixed by reusing code fragments, which provide a direction for APR techniques toward HDLs to search for the donor code. Furthermore, in the local scope, there's a still significant percentage at the local scope. It's about 11.7%. But the local scope can reduce the search space effectively. We could make a trade-off from the scope to search for donor code more effectively. Then we analyze the distribution of code clones or page contents in statement types to investigate which type statements are more likely to have a donor code. As shown in the figure, we found that the redundancy bug fixes are mainly distributed among a few statement types, such as process statements, assignment statements, and so on. It motivated the APR techniques for HDL to target some specific statements. Finally, please let me review our work. Firstly, we validated the redundancy assumption for HDL based on several open-source Verilog projects. Secondly, we perform analysis of distribution of redundant bugs fix. Finally, we developed an automatic tool vClone to extract and detect the clone for real-world bugs fix in Verilog projects. We hope that our study can help researchers to build the knowledge on how bugs in HDLs can be fixed, and our study can provide some insight for automatic program repair towards hardware description languages. In the future, we will study the effective APR technique to fix bugs in HDL by leveraging such knowledge. That's all. Thank you for your listening.